All right, it's 4 o'clock, so let's go ahead and get started. Hi, good afternoon, everybody. How's everybody doing today? Seems like some people are still rolling in. It's good. Nice. No. Yeah, that's the downside to the quarantine, is that you don't get to see too many people. But at least twice a week we can join virtually into this room, and we can learn about finite elements. Okay. So the plan for today is we're just going to have a regular lecture today, so there's no Ansys activity. So the topic for today is going to be verification and validation. So this is kind of almost like a part 2 of the lecture we had kind of right before the spring break, which was on mesh convergence. So mesh convergence kind of forms just kind of one part of what I call V&V, or verification and validation, but it's kind of part of a whole family of things that are kind of important to know. Okay, but before we get started with that, are there any questions on the Ansys activity or the project, or just anything about the class that I can answer before we get started? Okay. So I think one thing that I kind of left you guys hanging with last time was this idea of the hourglass energy. So I remember when we were doing our explicit dynamics simulation and we were looking at the energy profile over time, there's one entry there that said hourglass, and I was going to look that up so that next time I talk to you about it. So I looked it up. So I didn't get a super clear answer from what I saw, but what I do know is that sometimes when you run finite element simulations of structures, what can happen sometimes is that you get what's called spurious displacement modes. Okay. And what that means is that because of the numerics in the simulation, what can happen sometimes is you get some displacement modes that aren't real. Okay. And the reason they're called spurious is that unlike the real displacements that are actually occurring in your model, these spurious displacement modes do not produce any stress. So that's why they're called spurious. So even though they don't produce stress, what they do is that they do hold some energy associated with them. And when that occurs, then Ansys can actually detect that. Although it has some safeguards in place to kind of prevent this, because obviously this is not something that you want, because these spurious displacement modes aren't realistic. So Ansys already has some safeguards in place to kind of prevent these from happening. But if they do happen, then you can then it tracks them. So this phenomenon, and when it happens in finite elements, it's called hourglassing. Okay. And that's what that's the energy that that energy was tracking, basically, was some kind of just spurious displacements that aren't realistic. So obviously we know when you're running a dynamic simulations, you want these to be as low as possible. But if not, then you can do some things to correct it. Okay. Right, so the question is, why did these modes happen? So one thing that we that I kind of wanted to go over at while we were kind of in the beginning parts of the semester, but we kind of didn't have time, is this idea of numerical integration. In particular, the one that's used often in finite elements is a technique called Gauss Quadrature. Okay. So if you remember, kind of way back when we were working with the equations, that the finite element method is based off the weak form of a boundary value problem. So a weak form is basically an integrated form of those equations. I remember the reason why we did those integrations was so that we can do integration by parts and move some of the derivatives around to certain sites. Okay. So it turns out in finite element codes, that integration usually is not performed what's called exactly. So there's no actual, no one's sitting there and actually performing these integrals. What happens is that the code actually approximates these things with some numerical technique called Gauss Quadrature. The thing about Gauss Quadrature, there's kind of a lot of different ways that you can do it with kind of varying levels of accuracy. So there's kind of the same effect that we get for kind of the mesh refinement, where if you want more accuracy from your Gauss Quadrature, you kind of need to do a little bit more work and a little bit more computations. So what can happen sometimes if you're using a very low order Gauss Quadrature, so some terms you might see in some softwares. I haven't seen this in Ansys yet, but in other softwares you can definitely control this. As you can, it's often called reduced integration. And so what reduced integration, all that means is that you're approximating these integrals with some very low order, kind of low accurate scheme, which is really cheap because it doesn't take that many computations to do, but then you sacrifice some accuracy. And then what can happen sometimes is if you use reduced integration for structural mechanics, only in kind of certain situations, then this is kind of what leads to hourglassing. But it doesn't happen all the time. It only happens sometimes. And even but with this, there's still some safeguards that Ansys has in place to kind of prevent this from happening. So you don't see it all too much, but it's something good to keep in mind. So if you end up professionally, you're using a different software and you have kind of the choice, you need to kind of watch out for this setting right here for reduced integration, and make sure that you're doing more full integration to make sure that you're getting more accurate results. Okay, any questions on that? Yeah, so that's kind of a maybe not so short explanation to that phenomenon. So now now that makes a little bit more sense. So for some reason, the whiteboard feature in Zoom was disabled. So I'm using the Notepad app on my iPad. So literally, I have not opened my iPad until we started doing this virtual teaching. So I'm still kind of learning how to use it all that much. Actually, before this, I had given it to my dad because he likes to read his LA Times newspaper on the iPad. So I basically gave it to him. I said, "Here, Dad, Cal State Fullerton gave me an iPad. You can read your newspaper now." So right when things started going virtual, I drove to my parents' house, got the iPad back. So now I'm learning how to use it kind of for the first time. Okay, so let's jump into the lecture for today. So the lecture for today is on verification and validation. So a lot of times in the literature or just kind of in industry, you'll often see this abbreviated as V&V. Right? So if you hear the term V&V, what they stand for is verification and validation. Okay, so to kind of start, I kind of want to take a step back and kind of just think about finite elements as a whole. So we've done quite a few Ansys activities, and we're pretty far in the semester. So we can see that finite elements can be a really powerful tool to help engineers with their analysis. Okay. And so I underlined the word tool there to kind of emphasize the fact that it's in some ways, it's nothing better than any of the tools that you have in kind of your machine shop or in any kind of engineering lab. Just like, just to draw a simple example with the hammer, right? So a hammer is a very useful tool that we use, but there's a lot of ways to misuse the hammer. So you can, take the hammer and you can hit your hand with it, and that's, obviously the wrong way to do it. For finite elements, you can also mess it up in a lot of different ways. except it's not so obvious. You don't, you don't have a broken hand whenever you use finite elements incorrectly. Okay. And so in particular, what I want to highlight is that whenever you're doing finite elements or whenever you're using any kind of simulation tool in general, simulations are not reality. Okay. Okay. Doesn't matter how good your computer is. It doesn't matter how well meshed you are, and it doesn't matter, how good you are at finite elements. Simulations are never going to be reality. Okay. And in fact, we have kind of a general term for these. We say that it's simulations are a model for reality. Okay. So, even if you have kind of the best mesh in the world and you choose your boundary conditions as kind of as perfectly as you can, it's never going to be exactly matched up with reality. Okay. So ideally, we want the differences between our model and reality to be as minimized as we want those two things to be as close as possible. And we can minimize the errors between them by doing things like doing proper meshing and being careful about how we assign the boundary conditions. But no matter how careful you are, a model is never going to be the same thing as reality. Okay. So kind of give you an example. Okay. To kind of talk more about this fact for a model. So models, simulations are obviously a model. But there's, models is actually kind of a very general definition in engineering analysis or even scientific analysis. Okay? So let's talk about that a little bit more. So let's take an example where we have a cantilever beam. Okay. And then let's say that we're going to force the beam downwards like this. Okay. And say that, what we want to find out is what the maximum deflection in this beam is going to be. Okay. Okay. So there's several ways we can do this problem. So one way that we can do is we can simulate it in Ansys. Oh. My stylus stopped working. Huh. Well, that's weird. I'll make a new one. That was really weird. iPads are strange things. Okay, so we have our beam, so we have our force, and we want to find the maximum deflection. Okay, so one way that we can do this is we can simulate it in Ansys. Okay. And this will be a model of what's going to happen in reality, because obviously one thing we can do is we can just run an experiment. We can create or fabricate this beam, apply that force, and see what's going to happen. But a lot of times we don't want to run an experiment because that's expensive and that's time consuming, and you have to waste kind of a lot of metal for that. Okay. So one thing we can do is we can simulate it in Ansys, kind of as we know. But remember, a model is something more general than just simulation technology. So another way that you can model this this result is you can go to your 9-year-old cousin and just ask them, what if you have the situation, how much will the beam deflect? Okay. And believe it or not, when you ask your 9-year-old cousin that and he gives you an answer, this is the same. This is also a model. Okay. And so let's say your 9-year-old cousin, he loves the number 5. So when you ask him this, this problem, what he says is the answer is 5. Okay, and we'll put a box around that. Okay. So then you can ask him like 5 what? 5 inches? And then he'll just say 5. I like 5. Okay. So believe it, though, in both these cases, we were able to get some kind of prediction for the deflection in our beam without actually performing an experiment. So actually, both of these are models, at least, in the kind of general definition of the of the term. Okay. But as we know, depends on how clairvoyant your 9-year-old cousin is. The simulation in Ansys, that's going to be a better model. And so why is that? So the reason Ansys is more it provides the better model is that we know it's going to give more reliable results. Okay. And so how did Ansys get to the point where we can trust it so much? Well, first of all, we have to pay for it. So that's usually hopefully you get something reliable in what you pay for. But and the reason why you pay for Ansys is all the engineers and all of the computer scientists that that develop Ansys have performed what's called the verification and validation. Okay, so Ansys, like all commercial codes that you would hope, have been verified and validated. Yeah. So if your cousin's the smartest 9-year-old ever, then yeah, maybe you can trust him, and you can maybe start charging people to ask your cousin questions. Okay. So that's kind of just the gist of it. So just to kind of sum this up, verification and validation is kind of the processes that we as engineers undergo to kind of prove the reliability or the accuracy of our simulation. Okay. Okay, any questions on this before I wipe the board? Okay. So while I'm erasing this, what you'll see, and this is kind of true, kind of both if you go to industry with with simulation as your focus, or if you do research, is that the hardest thing that you'll have to do is actually not performing the simulations itself, but actually convincing people that your simulations are actually legit. Because what's going to happen a lot is that you can run your simulation and you can get your results, but people often are going to have a hard time believing you. So there's a saying that became very well known to me as I did my PhD. So my background is all in simulation work. Whereas if you do simulation work, and you're presenting your results, no one's going to believe your results except for you. But kind of the inverse is true if you do experiments. So if you do experimental work, everyone believes your results except for you. So if you're doing simulations, no one believes you. So it's kind of up to you to kind of convince people that your simulations are good and reliable. Okay. And the process in which you do that is with V and V. Okay. Okay. So now let's do some definitions. So we know what kind of the purpose of V and V is now, but let's kind of differentiate between the two. Okay, so question: Do they do hand calculations or gather experimental data? So there's kind of a mix of both. So kind of the best thing that you can do is as we'll kind of see later on today is to actually get experimental data to validate your simulations. But if that's not available, then there's still some other stuff that you can do to kind of provide some proof of reliability. Because if you kind of think of this as kind of like a court case, your simulations are kind of your defendant. And what you want to do with V&V is to provide as much kind of evidence to kind of defend your simulation, to kind of prove that they're good, that they're innocent. Okay, so the more evidence that you can get, the better that you can do. Okay. Yeah, that's a great phrase. Yeah, so the phrase that I've seen often is guilty until proven innocent. Yeah, that's a great way to kind of sum up kind of the how people feel about finite elements. Okay, so now let's do some definitions. If I could spell correctly. Okay, so now let's kind of go over the differences between verification and validation, because they sound very similar, but they actually mean kind of slightly different things. That's kind of why they're both in the name. So verification, kind of the definition that's out there is assessing the numerical accuracy of a simulation. Relative to the underlying equations. Okay. Because as we learned kind of early on in the semester, when we do finite elements, kind of the starting point is always some kind of a differential equation or some kind of governing equation. So there's a lot of things that you can do that you can mess up kind of in the weak form and the finite element form and kind of meshing that will make you solve that equation incorrectly. Okay. So kind of the way that I think of verification, or the way that I kind of remember in my head, is that verification is the process of asking yourself, are we solving the equations correctly? And so one example of this is, we've done this already. So, this was kind of the, the subject of our lecture before the spring break, is when we do a mesh convergence test, that's a form of verification. Hang on. So I cleared my kitchen table of glasses, but she was trying to bite through her bag of treats. Yes, the cat doesn't like finite elements, that's for sure. Okay, because remember what we're remember what we're doing with our mesh convergence study, right? So when we're doing our mesh convergence study, we can see that as we refine our mesh, then our solution gets more efficient or more accurate. So the underlying equations are still the same, but depending on our mesh density, we can either solve it poorly or we can solve it well. So mesh convergence tests, it kind of forms a very important part of verification. Okay. So that's verification. So next we have validation. Okay. So validation is also an assessment of accuracy. So it assesses the numerical accuracy of a simulation. Relative to the real life example. So some things that are kind of some considerations for validation are things like are we choosing the right physics? So if we're solving a dynamic problem as a static problem, then that's something that's going to lead us to incorrect results, and that's no fault of the computer. That's kind of our fault for kind of choosing some incorrect physics. Some other things that could lead to validation errors are using boundary conditions that aren't correct. So if you have wrong boundary conditions, that's going to lead to incorrect results. So you can solve the problem with those boundary conditions perfectly, but if the boundary conditions were incorrect, then your solution is going to be incorrect. Some other things could be like choosing the wrong material properties and stuff like that. Yeah, so user error. That's kind of a good way to put this. So kind of analogous question that I think about for validation is, are we solving the right equations? Okay. So these are often have to do with like was mentioned, decisions and choices that the user himself or herself makes. Okay. Any questions on this? All right. So the question is the mesh density in an analytical problem is the Gauss quadrature, or is it the domain derivative dx? So in an analytical problem, if you're solving it kind of without a mesh, then mesh density is not an issue. But so mesh density only comes in when you're doing kind of a numerical solution to a problem. Okay. All right. So I'm going to clear the board. Actually, let me just make a new one. Okay. Yeah, it's a lot easier. Okay. So now that we've gone over the definitions, let's kind of just be real for a second. So in truth, if you want to do kind of very careful validation and verification, it's actually a very long and laborious process. Because you're talking about kind of questioning kind of every aspect of your code and kind of every aspect of your decisions, and making sure that each of those is correct. So a lot of that can take a really long time. But the good thing is that if you're using some commercial code, mostly ones that you pay for, part of what you're paying for is you're paying for reliability, right? So when you pay for something like Ansys or Abacus or whatever other software that you're using, you can trust that all the engineers that develop this have kind of put in a lot of the work for you to do the verification and validation. Okay. So when you're using something like Ansys and you're using the static structural module, you can trust that the code within Ansys, it's going to be solving the equations of static structures exactly, or as well as it can be. So you don't have to go and verify that for yourself. Okay. And a lot of times in these commercial codes, they've actually validated against a lot of kind of benchmark tests and a lot of experimental data too. Okay. So a lot of it's done for you. So if you're going to be using Ansys either professionally or through research, just by saying that you're using Ansys, then there's a certain level of trust that comes with that already. So there's you don't have to prove absolutely everything because Ansys kind of already did that for you. Okay. But that said, whenever you apply finite elements to kind of a new situation or to your own personal, problems or your own personal situations, there's always some kind of, there's some potential for the solution to not match up with what you want it to do, right? Okay. So we saw that kind of already when we did our mesh convergence activity test, right? So even with a new situation or a new geometry, you have to perform your mesh convergence test to make sure that you have the right mesh. Even though kind of all the background stuff, Ansys has already kind of done that for you. Okay? So some common errors can be poor quality meshes, or also poor modeling decisions. Okay. So modeling decisions could be things like the boundary conditions or the material properties, or choosing the certain physics for your situation. Okay. Okay. And depending on or actually maybe I shouldn't say that. So if you're ever going to do finite elements for kind of anything, any professional or research application, some kind of V and phi will be required. Otherwise, no one's going to believe your results. And depending on the industry that you work in, the tolerances for or the kind of the expectations for V and V might be different. So in aerospace, where things are very tight, there might be a lot of stringent requirements on V and V. Okay. All right. So the question is, why do people bash on SolidWorks FEA package versus Ansys? I'm actually not sure too much of the history behind SolidWorks FEA. For me, I personally don't trust it all that much because it seems like it kind of popped out of nowhere. And it's something that I really don't have much personal experience with. I don't think it's bad. I think it's just that there's more. I think finite elements is something that's really specialized, and you kind of want to use like a really specialized software for it. That's kind of the impression that I get. Mm-hmm. Yeah, that's also true. Mm-hmm. Yeah, but I'll admit that I haven't played around with it all too much. But I think it's okay for some kind of more simple problems. But if you're doing something more complex, I think you kind of want a more specialized software for it. Yeah. Okay. Any questions on this before I wipe the board? Right. Right, so Scott says, just as an anecdotal, once at work we used SolidWorks CFD for a very complex problem. Took forever to run, but it was spot on to experiment that was conducted based on it. Oh, okay. So that's a a nice success story for that. Okay. Yeah, I just haven't really used it all too much. Okay, I'm gonna wipe the board. Okay. So let's kind of go on to kind of more specific instances of kind of what you would be expected to apply for V and V. Partly for the project, but also more so kind of for your professional life. So let's start with verification. So kind of like what we mentioned before, there's really not that much you have to do for verification because part of what you pay for the for the commercial software is that that the code will work well. So there's not too much that you have to do. But the thing that you do have to do that can cause the underlying equations to be solved incorrectly is if you have a poor quality mesh. Okay. Because as we've seen, if the mesh quality is not good, then that can lead to kind of incorrect errors, right? So if you kind of remember from before spring break, when we did a mesh convergence test, it looked something like this, where on the x-axis you have the number of elements, and on the y-axis we have our quantity of interest. So we'll call that QOI. Okay. And then what tends to happen is that if you have a coarse mesh, like kind of what we have in this region right here, okay, then you can see that as we refine the mesh, then our quantity of interest is changing. Okay, so that's not good. That's something that we don't want to see, because what's happening over here for the coarse meshes is that the software is kind of trying the best that it can to solve your solution as accurately as it can, but it just doesn't have enough to work with. It just doesn't have enough elements to give you that kind of accurate result. Okay. So in order for it to solve the equations well, you need to kind of give it enough elements to do so. Okay? So in particular, remember what we said before was that specifically for structural simulations, you want to make sure you have a refined mesh in the areas of high stress. Okay. Okay. So since we've already kind of talked about mesh convergence tests kind of at length, I'll kind of leave it at this. But I do want to give you one word of warning. You could come across this situation in your either your research life or your professional life where you're not going to use a commercial software. So you might use a research software. Okay. Okay. So there's some really good ones out there. So there's some really good open source projects that are properly verified and validated. So things that you might have heard of, some of these, like OpenFOAM is a good one. And those ones you can trust a bit more because they have a pretty large user base. But if you're using kind of a more niche software for a specific problem, you kind of have to do your due diligence a little bit just to make sure that you're doing that correctly. Oh yeah, yeah. We talked about that the other day. Yeah. So if you're using a research software that's open source, you have to kind of be careful with these. My pen broke again, but yeah. But just realize that with research softwares, especially the ones that you don't have to pay for, those haven't been as rigorously verified as like a commercial software. Mostly just because the team of people that are working on the software is pretty small. So I'll give you my own personal experience. So I worked on such a software when I was in grad school, and I will tell you that our development team, our QA team, our customer service team, our debugging team was me and one other guy. And we were, as grad students, we were pretty severely underpaid. So if you compare like two dudes doing all that work versus a company where they pay teams of people to do this, there's only so much that that manpower can do. So for those, you kind of have to be pretty careful with that. Okay. Okay. Any questions on verification? Okay. Yeah, and just like what Damien's saying is that, you know, when you're using research software or some kind of open source, the documentation is not that great too. So it's really, it's a lot harder than Ansys to kind of get off the ground than doing their tutorials. Trust me, because I've written the tutorials for our research software, and I've had a lot of complaints from people. And sometimes, you know, I got to a certain point, and I said, like, excuse me, you know, this was a free software, you know, I'm not, you know, I'm not paid all that much to be here, but, you know, let's just kind of do the best that we can. Okay, so let's talk about validation, because I think that's kind of the more interesting thing, you know, especially kind of for your projects. Okay. So there's lots of different flavors for validation, okay. Kind of with varying levels of goodness. So I'll talk about kind of the first one, which is kind of the best thing that you can do, is you can validate against experimental measurements. Okay. Because remember, the goal of a finite element simulation is to you know, best replicate reality as possible. So if you can, you know, have some real world evidence of, you know, showing that finite elements is producing the correct results, that's kind of the best kind of evidence that you can do. Okay. So in order to perform this kind of validation, you need to have some kind of physical measurements. Okay. You know, it depends, depending on who you talk to. Some people think that, you know, you can't have any kind of validation without some kind of physical measurements, because otherwise you're just playing on a computer. You know, that's kind of what someone's actually told that to me. Okay. So one kind of form to do this, you know, and the people at Ansys have done this, but if you're using a new software, this is something you would do, is you would actually perform an experiment specifically for this called a validation experiment. Okay. So the purpose of a validation experiment is to take, you know, a situation that you can simulate with finite elements and do basically the exact same experiment in real life. Okay? So there's, you know, kind of two, you know, aspects to this. Okay? So on the one hand, you have your you have a lab experiment. Okay? And on the right, you have your simulation. So the simulation could be FEA, it could be finite volumes, or it could be, you know, any kind of computational tool that you can think of. You can even validate, you know, some algebraic equations. Okay? So the idea is to you know, take this exact same situations in both, and, you know, show that you get the exact same thing. Okay. So in a simulation, you would set up the problem kind of exactly as we have. Okay. So we would set it up like, you know, you have your geometry, and you have your boundary conditions. Oh, question. If we cannot validate experimentally, can the measurements of a typical assembly? Yeah, so we'll kind of get there. So if you can't, you know, run this kind of validation experiment, which, you know, for most cases, you're not going to be able to run a validation experiment, validating against things like some published data, or, you know, or something that's similar that you do have data for, you know, that's, you know, usually pretty good too. Okay. So the geometry for your simulation will match perfectly with the geometry in your lab experiment. Okay. Okay. And then you'll try to set up you'll try to have your lab set up such that, you know, you mimic the exact same boundary conditions. Why is this happening? Ah. Oh my God. It's the cat, I swear. Okay, so you basically are doing basically the exact same situation both in real life and in the computer, and then what you should get is you should get the exact same thing. Okay. Okay. So let's do kind of just a quick kind of thought example just to kind of illustrate this. So let's say on the left we have our experimental setup of a cantilever beam. Okay. I know you guys are tired of cantilever beams, but they're easy to draw, so I'm going to keep doing it. Okay. And let's say that we have a force down here, just like before. Okay. And then what we can do is we can measure a couple things. So let's say that we put a strain gauge here. Okay. Such that we can measure the strain. Okay. And then let's say that at the tip we can use like a ruler to measure the displacement of the tip. Okay. So then we can take the exact same simulation and we can throw it into Ansys. Okay. And then we can simulate it. And then if we examine the strain here and then the displacement here, then what you should get is the exact same things that you measure in the experiment. Okay. Right. And if you don't get the same things, you can first of all make sure that your mesh density is okay. But if the mesh density is okay, then you can check to see maybe you implemented the boundary conditions incorrectly, or you didn't specify the material properties correctly, and things like that. Okay. But hopefully you would get something that's the same. Okay. Any questions on this? Okay. So that's validation when you have experimental data, but a lot of times you don't have that. And in fact, a lot of times you're running finite elements so that you can avoid running an experiment to begin with. Okay? So let's talk about validation without experimental data. Okay. So even if you don't have experimental data where you can, pinpoint exact locations where, you can match, the numbers with the measurements, there's still some things that you can do. Okay. So, one common way that people can do this is you can validate off some observations. So, a lot of times finite elements is applied to, to give you kind of a better understanding of a situation that that has already occurred. So there's some, observations either visually or you might have some data, and you might be running the finite elements to give you some insights on the things that you couldn't see or you couldn't observe. Okay. So what you can do is you can set up your finite elements to mimic that situation, and then check to make sure that you hit some certain things that you observe. Okay. So as an example, to kind of illustrate what I mean by this, there's the Space Shuttle Columbia that some of you may have heard of. Okay. Okay. So if you're not familiar, the Space Shuttle Columbia was a space shuttle that spectacularly kind of fell apart. Okay? And what happened was that when the Space Shuttle Columbia took off, what happened was that a piece of the foam insulation kind of fell off part of the shuttle and struck another part of the shuttle. And so what happened was when Columbia tried to re-enter the atmosphere, then the damage from that foam caused it to break apart, killing everybody on board. Okay? So as you can imagine, this was something that you don't want to happen. You don't want your multi-billion-dollar multi-billion-dollar space shuttle to break apart when it's coming back in orbit. So a lot of times, you want to run some simulations to better understand, what's going on, right? So FEA can be used to better understand, maybe the structural integrity of the foam. Okay. So this is a situation where you obviously can't run an experiment on this because no one in the right mind would let you blow up another space shuttle just so you can validate a finite element simulation. But what you can do is you can do some partial validation based on what you observed. So if you take the geometry of your space shuttle and you simulate the foam, if your simulation results can predict kind of the exact time and the exact kind of location where the foam broke off and kind of the damage that had occurred, then that's encouraging to say that your simulation, kind of the other things that you can validate will be good. Okay. And what this will allow you to do is allow you to analyze other aspects of the shuttle that you maybe want to better understand. Okay. Okay. Right. So I'll give you kind of a personal kind of story of kind of something similar to this, kind of based on the work that I've done. So a lot of the research that I've done previously is I've done simulations of blood flow, in live kind of human patients. So kind of just with the nature of that field, you can't stick a bunch of sensors inside a person to validate a simulation. But what you can do is you can check things like their external blood pressure. You can check what's called their ejection fraction, which is the fraction of blood that comes out of the heart. You can check their stroke volume. So there's some things that you can validate against, but you can't check the velocities of the blood kind of everywhere in the body, because no one really wants to put a ton of sensors inside themselves. So what I did, or one of my projects when I was in grad school, was to take those kind of loose set of data that doctors normally collect in the clinic, and made sure that my simulations were basically hitting those targets. And once you do that, then you can have confidence that all your other simulation results are going to be more accurate, they're going to be more reliable. Okay? So this might seem like it's kind of a niche thing, but if you're kind of creative with kind of the data that you have available to you, then there's some validation that you can do. Okay. Okay. Any questions on this? Okay. All right. So another kind of popular way to perform validations without kind of performing your own personalized experiment is to look in the literature and see if there's any similar experiments that you can do. Okay. Because if you're lucky, you might find an experiment that someone's done and they've collected some good data. And then you can use that data to validate your simulations. Because if you can produce kind of the exact same data that they produced, then that shows that your simulation, which is maybe not your exact problem that you're looking at, but it's something similar. Then that will be that'll provide some evidence that what you're doing is legit. Okay. Okay. And so, one other thing that you can do is if you're working for a kind of a big engineering firm, is that your engineering firm has probably done some experiments of kind of similar things as well. So if you can get your hands on some of that data that they have and show that your simulations can match that data, then that's kind of another way that you can validate your simulations. Okay. Right. Remember, all of this is just evidence, right? So, the more evidence that you can find to kind of, persuade people that what you're doing is actually legit, then that's always going to be a good thing. And especially early on in your careers when you haven't kind of, and you're kind of building up your, you're establishing yourself and you're getting people to trust you, the more verification and validation that you do, the kind of faster that people will be able to trust your simulations even more and kind of allow you to kind of move up in the company. Okay. So then what if you have none of the above? So what if you can't do an experiment and there's no published data, there's no observation that's even remotely close to what you're doing, okay? So this is the case if you have like none of the above. Okay. So this will be the case for a lot of your projects. You might be able to find some experimental data out there in the literature, but I'm guessing there's not going to be much available. So what do you do if you don't have any of the above? So unfortunately, what I'll say is that for if you're doing finite elements for research or you're doing it professionally, if you have none of the above, you're kind of stuck up the creek without a paddle. Because there's not much that you can do to convince people that what you're doing is okay. But there's still some things that you can do to do what I call sanity checks. Okay. Okay. And one way that you can do a sanity check is you can do what's called a simplified model. Okay. So this is something that you have to do for your project. So a simplified model is nothing more than just a very simple problem that you can solve on pencil and paper. Okay. Okay. And I put similar in quotes because sometimes you have to be a bit creative because a lot of times you'll have finite element simulations that are pretty complex and you can't come up with a simple problem. But you can at least try to get something that might be kind of close. Okay. And then what you can do from that simplified model is that if you compare that to your finite elements results, you should get something that's remotely similar. Okay. Given that you set it up correctly. Okay. All right, so then let's do an example. But before I write out the example, are there any questions on this? Right, so the question is, how similar should they be in general? So it's hard to kind of put a metric on that, and it's hard to kind of describe that in kind of in kind of general terms, because it's going to be really different for everyone's situation, and kind of very different for every application. I would say some kind of, so I can't give you like a kind of a numerical thing, but I can give you some heuristics that kind of I look for a simplified model. So first of all, I think the first thing is that you should try to get the geometry as similar as you can, without kind of getting too much into your simplified model. You should try to get this relatively the same dimensions. So the length should be the same, the cross-sectional area should be the same, at least somewhat close, right? So that would be kind of the first thing. And the second thing is, you should be able to set up the boundary conditions relatively the same way. So if you have a certain amount of force, that should be reflected in your simplified model too. Okay. If you're fixing at a certain point, you should be fixing it at kind of the same place in your simplified model as well. And then for the physics, you should pick an equation that kind of matches your physics kind of as well as you can. So that's kind of my thought process when I try to come up with a simplified model. And I'll kind of show you a really simple example, but and for you guys, I think for your projects, you're going to have to get pretty creative. But at the same time, I also know that not every situation is going to have a good simplified model, but I would say just kind of do the best that you can. Okay. All right. So the question is, do we use Ansys to verify our simplified results? You certainly can. I think that's a good thing that you can do, right? But I think for a lot, but for this project, I would say that you don't have to. I would say just try to get the simplified model to be as similar as you can to your complex problem. But if you do want to validate your simplified model with the Ansys results, I'd say that's a good thing that you can do too. Yeah, because it typically this is not really done that much in practice, because it's it doesn't really provide that strong an evidence of your finite element results. So there's not really a kind of a formalized way to do this, but this is just something I kind of came up with for the project, because I know for a lot of you it's going to be impossible to get your hands on any kind of data that's going to be relevant to the project. Yeah. Okay. So let's do an example with our favorite cantilever beam, right? Okay. And let's say that this beam has some body force. Okay. Okay. So here's kind of the situation that we want to model. So it's a very simple situation. It's not something that you would typically run Ansys for, but you can definitely do it. Okay. So one way that you can do this is you can do it with Ansys. Okay. So you'll throw a mesh onto it. Okay. And then you'll run your simulation and you'll get some results. Okay. So the other thing that you can do is that you can solve it with an equation. Okay. So here's an equation that you would solve with pencil and paper, and then this would be your simplified model. Okay. So you would take the results from your simplified model and kind of treat it as if that was your kind of your experimental data. So if you compare the results for your simplified model and for Ansys, they should get, well, in theory they should be the same, and for this simple situation it is. But I'll tell you right now for your projects that it's your simplified model is not going to be that great. So you should get results that are similar-ish. Okay. And again, making sure that, you know, at least the relative dimensions of your simplified model and, you know, the relative boundary conditions are roughly the same in between the two. Okay. Right. So I'll give you kind of some couple hints, just kind of based on, you know, what I saw people doing last year. So if you have kind of a pretty complex problem, which, you know, pretty much all of you have, it's going to be impossible to find a simplified case that kind of encapsulates all of it. So in that case, what I would suggest is you look at kind of a sub-component or a small part of your complex problem, okay? And then try doing a simplified problem based on that. Okay. So that's one thing that you can do. Okay. One other thing is you can try looking at some kind of heuristic kind of overall things. Okay. So one example that I can think of is if you're doing like a heat transfer simulation. One thing that you can do is you can you know, measure like the total volume and the total surface area of your model, and then come up with a simplified model that has the same volume and surface area. And if you observe or you kind of solve the equation, that you get like the same energy flux that comes out of your simplified model as your Ansys one, or at least something similar, then that kind of also validates, counts as like a simplified model validation. So be creative here. You know, try to you know, find something in your model that you can validate against, or at least do a sanity check against some simplified simulation. Okay. So the example I have here is a differential equation, but it doesn't even have to be that. Okay. So if you have some kind of algebraic equation that you can use. Okay. You know, that works as well. You know, as long as it's some kind of calculation that you can do that relates to your project that's done outside of Ansys, then that works for me as some kind of simplified model. Okay. So for some of you, I know that you do have experimental data that's going to be accompanying your project. So if you do have some kind of data, or if you do have some kind of observations that you've either done previously for your senior design project, or you can look up either online or through the literature, then that counts as your simplified model too. So if you have kind of better ways to validate your project, then I would want you to use that. But the simplified model is kind of the last resort, where if you don't have any of the above, any kind of experimental data or any kind of published data that you can use to validate. But I just want you to perform some kind of validation for your project. That was kind of the idea for this. Okay. Okay. Are there any final questions on this? Okay. So from here on out, you know, we're still going to have some lectures, but you know, today ran a little bit longer than I thought. But I expect these lectures aren't going to last the full time, because usually this is the part of the semester where you guys are kind of working on your projects, and I usually like to go around and kind of help you guys. But you know, obviously we can't do that. But you know, these lectures are still you know, going to be kind of relatively the same length. So I'm guessing these lectures will probably be in the range of like 45 minutes to an hour. And then there will be some time after the class. So, you know, we've got 6 more minutes left today. So if you have questions on your project or just questions about anything, then, you know, I'll stick around until the end, you know, for you to answer, to ask them. Okay. But if you have no more questions, then you know, I'll say goodbye to you guys for the week. So have a great weekend. Please stay safe and please stay healthy. And then after this, we got 4 more weeks to go. Okay? So don't forget to do Ansys Activity 5. So that's going to be due next Thursday, so a week from now. And then next Thursday, we're going to do our next Ansys activity, which is shell and beam elements. Okay. Okay. So if you have no more questions, then I'll talk to you guys. I'll see you guys on Tuesday. Yeah, that's a good question. I would say kind of the first thing that I would do is kind of just simulate it as kind of just like a block, you know, that you kind of see rolling down a hill. So like say, you know, you have some block. God damn it. And then this block, you know, if you kind of push it along, it's going to have some friction forces. Okay. So if you can kind of compute, for your case, kind of the normal force of the piston that's kind of, you know, exerting against the shaft walls, then you can multiply that by some frictional coefficient. And, you know, I think the tricky part there was kind of, it would be kind of estimating that normal force and seeing, you know, if that's going to be accurate or not. Yeah. Yeah, that's tricky though, for sure. So today I don't have office hours, but I can stick around for a little bit if you want to talk. Oh yeah, yeah. I think you know, I think just probably just can go one step at a time, and we'll kind of deal with problems as you know as we come up with them. But yeah, it's good to kind of be aware of all those things for sure. Louis, did you want did you want to show me something on your computer now, or did you have questions about something else?
Yeah, I had a question about how to apply load on my model, more or
Sure.
less.
Okay. Yeah.
Is there a way to share screen or something?
I think I have to enable it. Let me see.
Okay.
Okay. Yeah, I'll give it a try.
Okay, definitely. You want to continue? Yes. Okay, sure. So far, I have to kind of induce a moment on this.
Okay.
So I'm just trying to figure out how to do it. So I was watching some videos online on their suggestions, and their suggestions is, for example, you see these patches.
Yep.
So these are holes that connect to our suspension system.
I see. Okay.
So I don't know if it would be adequate to apply, for example, a load on this hole, right? So like we would
Oh.
apply a load on all these holes up, and
Uh-huh.
then the other side of the chassis, so this side of the chassis, it would be down. So it would induce a couple. So a force down here,
Uh-huh.
and a force up on the other side. I don't know if that would be accurate.
I think at least I think that's a good starting point. I think, you know, if you have the whole geometry there, then I think you should definitely use that to basically apply the forces like that. I think that would be a reasonable way to start. I mean, the nice thing about, you know, finite elements is you can always try some stuff, and then if the results don't look like kind of what you would expect, then you can always change some stuff. But that sounds pretty reasonable to me, on how to start that.
Okay, for sure. And then just one more thing. So the way so on the Solidworks model, for example, like they would, uh, for example, model the suspension as a rigid body.
Okay.
The thing is, like, I don't know if that's out of the scope by now because I feel like that's like another kind of like another project to do, like in its
Oh,
own self.
to basically to verify if those rods are actually rigid.
So it would be more or less. So an alumni told me that he's done this before. What he's done was how do I say this? So he used beam elements on the suspension,
Okay.
and then he applied a coordinate system on this hub right here,
I
somewhere
see.
here, and then
Uh-huh.
he would apply the directional force from the hub.
To the rods, which are beams, and then
Yes,
that
and
would force that.
yeah.
I see. I mean, so we're gonna do beam elements in the next Ansys activity. So we're gonna learn about that next Thursday.
Okay.
Um, so I mean, I think, you know, it would be possible. It's just that there's a lot of small elements that there's a lot of small parts I would say here.
Oh
Um,
yeah. Yeah, I wouldn't
that's
put all this. What I would say is, you know, I would probably connect this beam to the chassis itself.
I see. I see.
Yeah.
Yeah,
And then
I think if you do want to model those rods as beam elements and apply the loads there, that would be more accurate. And actually, you know, you can do a comparison. So you can compare kind of the situation that you talked about before, where you apply the loads directly on those holes, and you compare the results where if you do it with the beams, and see, you know, how that affects results. I think that would be
okay,
something interesting to do too.
definitely. Okay. And then I think kind of like the last question would be so these holes would this cause some sort of like problem with the mesh at all?
Yeah, those holes are really tiny, and I'm actually kind of surprised that the mesher was able to do it.
Yeah.
So what I would do, because those holes are so small, is I would apply a mesh refinement around those holes.
Okay.
Because what you don't, because like the as you can see, like some of those triangles around the holes are really skinny.
Yes.
So
Yes.
when you have like really distorted elements like that, that can cause some errors. So if you can refine just around those holes, I think that would help it a little bit.
Okay. Okay. Definitely.
Yeah.
I think that's everything I kind of needed. Thank you.
Okay. Yeah. Give it a try, and yeah, let me know. I'll try to, you know, reserve at least, you know, 15, 30 minutes after each lecture so that, you know, people can talk about their issues like this.
Yeah. Okay. Thank you so much.
Yeah.
Appreciate it.
No problem. All right. Does anyone have any more questions? If not, I'm going to sign off and start cooking my dinner. Okay, so if you have any more questions, you can definitely send me an email. If not, then I'm going to sign off for today. Okay, so the video for this lecture should be up probably by tomorrow morning. Okay, all right, bye everybody.